just an announcement that the meeting is being recorded now. So if you have any questions, I would suggest you raise your hand, and then I can unmute you so you can ask the question. Alternatively, you could also type it in the Q&A box. So with that, let's get started. Chaitali, do you want to take it away?
Mm-hmm. Yeah, thank you so much, Srujan, for the nice introduction. I'm Chaitali, and I'm a new postdoc in the electrical engineering department. And I'm very excited to talk to you about work that I did as a graduate student with Alexander Gaita and Mikhail Lipson at Cornell and Columbia. So about questions, I think I'll stop a midpoint and answer whatever questions people might have. So I'm going to start by asking the question, why should we care about making quantum systems with optical photons? Well, the reason is that optical photons are the only flying qubits that we know of. So if you look at the leading platforms for quantum information processing, such as Rydberg atoms or ion traps or superconducting microwave circuits with Josephson junctions, they all feature very high nonlinearity. And this makes it easy to implement deterministic two-qubit interactions with these systems. However, this nonlinearity comes at a price. These systems are not only interacting strongly with each other, but also strongly with the environment. And so they're either sitting in optical or electromagnetic traps or inside dilution fridges. And it is certainly not easy to, let's say, make 5 dilution refrigerators talk to each other, even if they're sitting in the same room. So this is where optical photons come in. Due to the relatively high energy of visible and infrared photons, we can actually transmit them over long distances in free space or fiber optics networks without adding any thermal noise at room temperature. And we have seen flying qubits in action in the last 2.5 decades, starting with the first demonstrations of quantum teleportation that probably happened on a single optical table. We have now evolved to much more sophisticated experiments. This particular demonstration from Anton Zeilinger's group in 2012 showed teleportation over the Canary Islands in Spain that are 143 kilometers apart from each other. In 2020, it's gone even further ahead, and this team in China from Jianwei Pan's group has managed to put an entangled photon pair source on board this Messier satellite. And recently they published a paper where they do quantum key distribution over 2 cities that are separated by more than 1,000 kilometers. And all these experiments were done with photons at around 800 nanometers. Okay, so optical photons are clearly carrying information over large distances at the scales that we would like to. And these previous experiments, they were done with polarization entangled photons. In this talk, I'm going to talk about frequency encoding, where I mean that I'm encoding a qubit in 2 different energy states of a single photon. And how we can do operations with this using nonlinear optics. And the reason I want to talk about this kind of frequency encoding is that we do know that for classical networks, we have very efficient hardware in terms of fiber optics, WDMs, integrated photonics that is compatible with frequency division multiplexing. And this has this hardware is very low loss, very inexpensive, but it has not been exploited for quantum applications yet. And what I want to show is that by using tools from nonlinear optics that are simple and well understood, we can actually bring these advantages to the quantum regime. So let's look at what tools would we need for building an all-photonic quantum network. We would need very high quality and deterministic single photon sources. We also need to be able to do 1 and 2 photon gate operations with these. We need to store these photons in some, preferably at room temperature and in an active fashion, and we need efficient single photon detectors. And if we do have these ingredients, we can potentially create resource states. For instance, we can create cluster states that have recently been proposed as a replacement for matter-based quantum memories in quantum repeaters. So in our group, we've tried to bring these different resources that we need to our expertise, which is nonlinear optics and integrated photonics. In particular, we've demonstrated a frequency multiplex single photon source and single and two photon operations with these color qubits that I'm going to talk about. And we can also perform, we can also store these photons for a relatively long lifetimes using high quality microresonators. So I'm going to describe these various ingredients in the rest of my talk. So first, I'm going to start with a brief overview of quantum frequency conversion and how we do this in a commercial dispersion shifted fiber with close to unity efficiency and with very low noise. And this is really the key ingredient that allows us to do all the other applications that I'm about to describe. The first application I'll talk about is how we can use this process as a efficient frequency switch and make a frequency multiplexed single photon source. The next application I'll talk about is how we can actually get two photons that are distinguishable at first of different colors and how we can create a frequency beam splitter with this quantum frequency conversion process and show Hong-Ou-Mandel type interference. And finally, I'm going to describe a cool application that is for temporal mode processing and show how we can use four-wave mixing for resolving single photon waveforms with picosecond resolution. So as I mentioned before, what I mean by a color qubit is we are encoding our qubit as let's say a blue or a red a wavelength shown here. And we have, unlike classical applications where we wouldn't want these different frequencies to interact, we don't want crosstalk between different frequency multiplex channels. But for quantum applications, we do need to actively switch between these two states. And for this, we cannot rely on passive linear optics. We need some nonlinear process. And for this, we will use four-wave mixing. And I will show how you can implement four-wave mixing to implement a two-mode coherent unitary transformation between different color states. So why do we want to use four-wave mixing and not other nonlinear processes? The reason is that let's say we try to use electro-optic modulators, that bandwidth is very limited, and they also have at least the commercial ones have a significant loss. And if you try to use electro-optic modulators, their bandwidth is probably like 10 gigahertz. And even if you drive them super hard, you're probably not going to get a lot of conversion from one band to the other. In addition, you always generate sidebands with electro-optic modulators. On the flip side, if you're using sum and difference frequency generation, in order to satisfy energy conservation, you have to place them in two different optical bands. And so these are not exactly compatible with WDMs or integrated single photon sources, and it makes it harder to scale systems with these. So with four-wave mixing, we actually have one additional degree of freedom, is another classical pump, and that allows us to do frequency conversion over a bandwidth of 100 gigahertz to 2 terahertz, and this is 100 gigahertz to 2 terahertz, and this is the frequency range of WDMs and integrated photon sources, and I'll show how this compatibility works out quite well. So the process that we have used for quantum frequency conversion is Bragg-Scattering four-wave mixing. So in a Kerr medium, we have 4 interacting optical fields. And of course, the processes have to satisfy energy conservation and phase matching. And to make the process selective, we make the phase matching selective. So in our particular application, we want to switch between a blue photon and a red photon. So we make the other two pumps strong and undepleted. and the other two fields can be at the single photon level. So here I've written the effective Hamiltonian of such a process. And if we can actually manage to phase match, we get an effective two-mode unitary interaction between this red and blue photon. So this kappa here is proportional to the interaction, to the Kerr coefficient of the nonlinear medium, and inversely proportional, obviously, to the mode volume. A stronger confinement gives you stronger nonlinearity. And also directly proportional to the field strength of the two classical pumps that they're not quantized anywhere in this equation. So so if we solve these this simple Hamiltonian, we get these coefficients, and I've just put them down here for completeness. But essentially, the message is that if we have a completely phase matched process, we can actually get full conversion from this blue photon to the red photon exactly as we want. Or if we tune the relative phase of the two pumps, we can get rotations along the equator on the Bloch sphere, and we can also control the pump power to get whatever splitting ratios that we like. So now the key to making this process efficient is that we want this to be the only nonlinear process that is phase matched. We don't want any spurious nonlinear processes. And we also don't want any noise from our strong pumps. And so we do this process inside a commercial dispersion shifted fiber. And here I'm putting down the phase mismatch. It has two contributions, one from the chromatic dispersion of the fiber, and second is the nonlinear phase mismatch. This is coming from self and cross phase modulation of the pumps. And it is easy to kill this term by setting the pump powers to be equal. And so now let's look in more detail of how we can kill this chromatic dispersion term. So if we place the pump fields and the single photons symmetrically about the zero dispersion point of our fiber, and we just Taylor expand this for higher order dispersion, we see that the phase mismatch, the linear phase mismatch, is proportional to beta 3 times this asymmetry parameter that I've introduced here, which measures how far are the single photons separated from as compared with respect to the zero GVD as compared to the pumps. And you can see that when this parameter goes to 0, we can this term also goes to 0. What we're left with is some fourth order terms that are rather weak. So this is the measured dispersion of our fiber. So we place our two pumps at 1.55 microns, where we have erbium doped fiber amplifiers that can amplify our pumps, and we put our photons at near 1.3 microns, where we are still in the O band and can use like commercial WDMs, etc., that make our experiments low loss. The feature that I want to emphasize here is that we are only phase matching a single sideband. So as long as our phase matching bandwidth is smaller than this separation over here, we will not phase match the other sideband, and this is what, and that is necessary to get close to unity efficiency. If both sidebands are phase matched, we'll obviously be limited to a 50% efficiency, which is a problem in many other implementations of this process. And if we want to use this process at the single photon level, we need to make it very low noise. So these are the potential noise contributors at the single photon wavelengths from our strong pumps, and we see that the Raman noise is potentially what would contribute the most, and even at room temperature, it's quite low because the anti-Stokes band gets significantly suppressed 200 nanometers away. It can be suppressed even more by cooling down the fiber with liquid nitrogen. But even at room temperature, we have less than 10 to the minus 5 photons per pump pulse. And so we can truly use this process with single photon input states as we would like to. And here are our experimental results. So it matches very closely with the theory predictions that I showed before. The conversion efficiency we get is about 97%, and this is only limited by the bandwidth of our input. If we use a narrower bandwidth, it could potentially go to more than 99%. You can see that that there are no other spurious nonlinear processes that are degrading this performance, which is exactly what we would have liked our phase matching to do. And the process is selective but simultaneously tunable, which is what makes it useful. So here I'm showing that I am tuning the frequency separation between the two pumps from 700 gigahertz to 1.7 terahertz. This is about 10 WDM channels, and we can see that the efficiency is still maintained at more than 95%. We do see a reduction in the bandwidth by a factor of half. This is due to higher order dispersion that we discussed before. So now that we have this very nice tool in our hand, what can we do with it? So the first application that I'm going to talk about is how we can make a frequency multiplexed source with this. So as mentioned before, if we want to make large-scale quantum networks, we need millions of identical single photon sources, hopefully operating at room temperature, that emit indistinguishable photons, and also that are very low, have very low contamination of multiphotons. But as mentioned before, the weak nonlinearity of dielectric media that leads us to rely on probabilistic operations also makes it very difficult to generate highly non-classical states of light with these dielectric media. So there's been a lot of progress in making single photon sources, especially over in the last 5 years. Quantum dots have emerged as a great source. They have solved a lot of their problems, such as blinking and dephasing and a lot of other problems that they used to have. And they've improved their extraction efficiencies and the indistinguishability of successive photons from a single quantum dot. But it is still difficult to tune these quantum dots to a wavelength that you would like it to. And especially for photonic applications, this is very important. You want your source to operate at the wavelength that your experiment needs and not the other way around. And also for quantum dots, it's still very difficult, let's say, to make 5 quantum dots that are indistinguishable from each other. So this is where where parametric single photon sources can be advantageous. You can tailor their spectral and temporal properties by modifying your phase matching conditions and by using different kind of crystals and pumps. And you can tailor them, make them for your particular experiment. And in particular, at least in this work, we use silicon nitride sources to generate these photons. So these sources are also compatible with integration. So here is a brief overview of down conversion, which is what people have typically used in the last 25 years in quantum optics experiments. So we basically have a pump, again, that is undepleted and can be treated classically, pumping a second order nonlinear crystal. Here it's typically a periodically bold lithium niobate or bismuth borate or something like that. And if the process is phase matched, this spontaneously generates two photons, and these photons are time energy correlated. So if I see a photon in one arm of the detector, I know that there is a photon in the other arm. Of course, there can be errors due to losses, but I won't go into that right now. But if you look at the photon statistics of emitted from such a source, we see that the statistics are actually thermal. So most of the time we are not emitting a single photon, we're emitting more than one photon, or we're emitting nothing. Basically the maximum heralding probability is limited to 25%. So even if everything was perfect, our detectors were perfect, and we had photon number resolution, etc., we would still only get a single photon 25% of the time. So how do we overcome this? We can use active feed-forward. So we can use many of such probabilistic sources, and then use a switching network that is watching which of these probabilistic sources is heralding a photon, and then use this switching network to route all the photons to one common target output. And the reason why this works is that we can now operate each of these sources at a much lower pump power. And this reduces the multi-photon emission probability while increasing the single photon emission probability. Now, the biggest problem in actually scaling this scheme to the deterministic regime is the switching network. We need a very low loss switching network. So let's assume that we had a lossless switching network and we did all the calculations. We see that with a detector that tells us whether we heralded one photon or more than one photon, we can actually get deterministic operation with just 17 multiplex sources or modes. So this is promising, but the hard part is to keep the loss of the switching network low. So people have realized these and shown many promising demonstrations, especially from Paul Kvyat's group with his temporal multiplexing. But the problem with both of these is that the switching loss increases as you try to multiplex more modes. What we try to do in our source is that we try to break this limitation and implement a source where the number of where the total loss of the switching network does not scale, no matter how many modes we are multiplexing. And so we take a broadband single photon source and we carve out narrow channels via heralding. And this heralding information tells us which channel, which frequency we heralded a photon in. And then we use Bragg-Scattering as a tunable frequency switch to route them to one common target output. Now, why does this not scale in terms of loss? The reason is that we are putting all the complexity of loss and switching onto the Bragg-Scattering pumps. So this is a cartoon of what an implementation with Bragg-Scattering would look like. We have our heralding single photon source, which can be just a single broadband bulk source or an integrated ring resonator source. And then we have these Bragg-Scattering pumps that for the switching. And so if we want to add more modes, we only have to add more Bragg-Scattering pumps. And of course, this adds loss and complexity on the pump side. But on the pump side, since the pumps are classical, we can amplify and overcome loss very easily. And this is essentially what we are exploiting in our scheme. And here are some calculations that illustrates this advantageous scaling. So assuming some optimistic 85% loss per switch, we see that for these other schemes, we saturate at a heralding probability of less than 50% and less than 10 multiplexed modes, whereas for our scheme, it actually follows the trend line of a lossless switching network. Now, this trend line is not going all the way to 99%. That's because I'm assuming detectors that are not photon number resolving, and this performance gets better for all sources if we just use a detector that tells us whether it was one photon or more than one photon. And I'll describe that we have such detectors later in the talk. So the single photons, we implemented this with a bulk Piplin source, and this is our experimental setup. We pump with green light and generate correlated photons at 940 and 1300 microns. We carve out 3 narrow frequency channels from this from the heralding arm, and we use this heralding information to drive an FPGA that is then driving our Bragg-Scattering pumps. So depending on which channel we herald a photon in, we turn on the correct set of Bragg-Scattering pumps. So if we herald a photon in at omega 0, we keep the pumps off. If we herald one at omega 1, we turn on pumps 1 and 2. And if we herald in the last channel, we turn on pumps 1 and 3. And all this results in these photons to be switched to one common target frequency that we extract via filtering. And then we measure coincidences with our heralding signals that we recorded before. So we did this with 3 channels, and here are our results. So with 3 channels, we should ideally get 4.8 dB, but we do have splicing loss that results in 1.3 dB total loss, but it's still low, but can be improved even more by reducing the number of splices in our setup. And we get a total enhancement of 3.5 dB with just 3 sources. And a relatively high single photon generation rate. Now we want to make sure that we are not adding a ton of noise with our Bragg-Scattering pumps while doing this multiplexing. So we measure the noise properties of our source. So here I'm showing the coincidences to accidentals ratio as a function of the heralded photon rate. And we can see that for the multiplex source, the signal to noise is twice as much for all heralded photon rates, and is still relatively high at about 100 for the maximum heralded photon rate. And we see a similar trend in our G2 measurements, and we see that the multiplex source has a low G2 of about 0.07 at our maximum photon generation rate. So for these generation rates, we are driving the Bragg-Scattering pumps at about 1 megahertz. So this shows us we can drive them at high repetition rates and without adding a lot of noise, and that this multiplexing is actually successful. So of course, I just showed 3 channels. In order to scale, we need a lot more than that. And the measurement that I showed you before shows that we can actually do that without reducing our switching efficiency. We do lose out on bandwidth as we go to larger separations between the Bragg pumps, but it's still more than 50 gigahertz and more than sufficient for let's say using this with an integrated single photon source. So one measurement that I did not show here is that of indistinguishability, which is very important for quantum applications. So the reason for that is that we were using a long Piplin crystal that results in this tight joint spectral amplitude, and we could use a shorter crystal to get a factorizable joint spectral amplitude. This would obviously reduce the brightness. A much better way to do this is to use microresonator based sources, where it is very easy to modify the geometry, in particular the coupling condition of the ring with the bus waveguide, to get photon pairs with more than 99% spectral purity. So I would like to stop and answer any questions if anyone has any.
Folks with questions, yeah, please feel free to raise your hand and I can unmute you so you can ask your question. Okay, we have our first question.
So if I'm the one who's asking, you didn't say anything that I caught, but maybe I missed it, about Raman scattering.
Mm-hmm, yes, I do have.
Nitride, silicon dioxide, any of these low loss, wonderful materials have, when you start looking at 2 photon correlations at one wavelength and another, the the power levels associated with the probability of getting extra photons is not negligible. So what are you going to do about that?
So actually in silicon nitride, we have made a lot of measurements at the single photon level. We have not seen evidence of Raman scattering in silicon nitride. It is indeed a problem in silicon, and definitely we do have Raman scattering in our Bragg-Scattering fiber, because that's just silica. So we do have Raman scattering, and the measurement that I showed before was about that.
So what's the probability when you've made one photon, and then I integrate over a terahertz, which is the kind of bandwidth you're after, that there's what's the probability of having one photon spread over that bandwidth? Just to get a more quantitative statement of what no evidence is. I mean, you can't just look in a little bandwidth, right? You're interested in Raman scattering as a broad bandwidth. And so what's the probability over a bandwidth that's relevant to you in experiments?
Oh, over a bandwidth that's relevant to me. So, well, yes, I mean, in an integrated photon source, if I'm looking at just the photon source, our bandwidths are about 200 megahertz for one of the photons. And so it's quite negligible. I mean, we just haven't, we've tried to make very, very sensitive measurements to pump our samples very hard and try to see any evidence of Raman scattering. And we have not seen it either at 1.3 microns or 1.5 microns. And I mean, there are other groups that that you do use silicon nitride at maybe 1 watts of powers for generating frequency combs. They see some indirect evidence of frequency shifts and stuff like that. That may be evidence of Raman scattering in silicon nitride, but we haven't, for the power levels that I use maybe 1 or 2 milliwatts to pump my source. And I haven't seen this in my measurements, because I would totally see it in my interference measurements. As background noise, if it exists.
No, not necessarily, because you're looking at interference over a gigahertz. And I'm interested that your photons at one frequency, and then you go a terahertz away because you're interested in broadband sources ultimately. So you're looking at very low spectral densities for the photon. This isn't as easy a problem as you made a photon in omega 1, and the other photon, the noise photon of Raman scattering, only comes at omega 2. Well, that's easy to go look for. But if you've got a gigahertz bandwidth with your photons, and there's a phantom photon that you don't really want, that's spread not over a gigahertz, but over a terahertz, and the spectral density is down, 1,000-fold. So it's not a trivial measurement to make, but they're there, I guarantee you.
In silicon nitride? Well, okay, maybe. Okay. Well, I don't know. We have not. Yeah, I mean, the only way we've tried this is. I mean, I haven't seen it in my.
It's hard to see. It's a very small background.
Okay.
Very low spectral density.
I see. Okay.
Right. I have a question from my end. So in this frequency multiplexing scheme that you're talking about, you have this advantage of a fixed loss, but it looks like in your experiment you're using multiple lasers.
Yes.
I think the number of lasers might scale linearly with the number of.
That's correct.
Frequency bins. So have you thought about I don't know, ways around this resource scaling? Which
yes. So that's a good question. But so one way to do this is to use lines from, let's say, a frequency comb. So this was a first demonstration, and obviously is not very resource efficient. But let's say you can totally use a frequency source. So here, and if that is compatible with an integrated photon source, and then like your frequency separations between the photons and the pumps would match. and this is totally possible to do. So of course, you would still be limited by how much amplification you can get with one amplifier. You would need more amplification, that is for sure, because you cannot send 10 pumps. They would all saturate at the same power, so that's not useful. But EDFAs are not that expensive, and what we're looking to scale is to maybe 15 to 20 modes, and that doesn't look impossible. So.
Okay, thank you. If there are no further questions, we can move on then.
So the next application that I'm going to talk about is quantum interference with this frequency beam splitter that I just described. So Hong-Ou-Mandel interference, which was first observed in 1987, is a signature effect in quantum optics. And essentially, when we have two wave packets of photons that are impinging on a 50-50 beam splitter, and we look at the outputs. If we have the two outputs where both photons are transmitted or both photons are reflected, if these output amplitudes are indistinguishable, then we see that both photons always come out of the same frequency arm. Now, this picture might be a little misleading because this is a two-photon interference effect and does not depend on the phase of the interferometer. So even if we propagate the photons for much longer than their coherence time, we would still observe this effect. And this is what we see in our experiment. Of course, this has been a two-photon Hong-Ou-Mandel interference is fundamentally interesting, but also a necessary component of many protocols such as Bell state measurements or cluster states or fusion gates for cluster state generation. So as I mentioned before, we can use Bragg-Scattering not just as a frequency converter, but also it's a two-mode unitary transformation because we have suppressed other competing nonlinear processes. And so we can drive the color qubit anywhere on the Bloch sphere. And so we can tune the relative phase of the pumps and the power and the interaction length to get a tunable frequency beam splitter. So we set the power to be a 50-50 beam splitter for this particular experiment. So this is what I was describing before, is that we have single photon sources made of silicon nitride. These microresonators have quality factors that can go from 1 million to about 5 million. And we can pump them to generate very narrowband single photon sources. And what in this experiment, what we see is that if we match the frequency separation of the of two selected photon pairs from this resonator exactly to the four-wave mixing pump separation, we see that both photons always exit with the same color. And this is interesting because, as I said before, this is truly a two-photon interference effect in that the coherence time of our photons is a few nanoseconds, but we propagate the photons for about 100 nanoseconds in this fiber, and we still see this interference. So we are generating photon pairs using spontaneous four-wave mixing. So here inside a cavity. And the reason why it's nice to use these microresonators is that it is easy to tailor their dispersion by modifying their geometry, and also to change the coupling condition by modifying the spacing between the waveguide and the resonator. So using this very simple geometry, we can actually realize different kinds of we can realize different brightness, overall brightness of our source. We can also, by coupling this bus waveguide at multiple points in the microresonator, like I described before, you can actually change the relative coupling condition of the pump and the photons to get different kinds of spectral purities from these photon pair sources. And with these high Q resonators with quality factors in the range of a few million, we can get photon pairs that have a coherence time of a few nanoseconds, and with bandwidths that are going from 50 megahertz to a few hundred megahertz. So this is our experimental setup, and I'm measuring here the again the coincidences to accidentals ratio, and this is more than 60 for our particular implementation. And we have used a feedback loop here to keep the microresonator at a fixed detuning with respect to our pump laser, and this is important for this is important for continuous data acquisition over long periods of time in order to collect sufficient statistics to observe the interference that we want to. And secondly, we need to know the free spectral range of our resonator down to its much less than its line width. And for this, we use a phase modulator and make a transmission measurement of our resonator to see to precisely measure this frequency separation, and we measure it to be about 805 gigahertz. So our setup is stable for more than 8 hours, and we know all the properties of this. So let's look at what we would need to observe interference of these two photons that are now separated at 800 gigahertz. We impinge them on our frequency beam splitter, and now in order to see perfect interference, we want that the probability amplitudes where neither photon changes its color or both photons change its color, we want these to be indistinguishable. Here, as a reminder, capital omega is the frequency separation of the Bragg-Scattering pumps. So now if we look at the second order correlation that we measure between the red and blue photons, we see that it's the Fourier transform of the difference of these two photon amplitudes that we compared before. And when these are indistinguishable, G2 goes to 0 for all time delays. And for other frequency separations, we observe quantum beating. So in general, this is difficult to evaluate, but we are using a CW pumped resonator. So this delta function is, so we can easily write this joint spectral amplitude as a product of the delta function that represents our CW pump and a product of these two Lorentzian amplitudes. Their modulus squared is essentially the cavity Lorentzian. And if we look at the quantum beating that we observe is essentially a function of the frequency separation of the photons that we started with and the frequency separation of the pumps that in the four-way mixing process. And we get a very neat expression. So this double exponential is just the Fourier transform of a Lorentzian. It's modulated by this beating signal depending on this detuning. This is our experimental setup. We combine our photon pair source with the Bragg-Scattering four-way mixing that we had, that I described before. So now our photon pair source is not synchronized in time with our Bragg-Scattering, but we use post-selection to get around this. And then with the same data file, we can actually extract the background in time windows that are actually not synchronized with the pumps and compare them where the photons do see the presence of Bragg-Scattering pumps. So we essentially perform a threefold coincidence measurement to extract our interference curves. And these are our results. So when we are close to zero detuning, our lasers are fluctuating by about 30 megahertz. So we are close to zero detuning. We do see a complete the two photon coincidence rate completely disappears when the photons are actually seeing the Bragg-Scattering pumps. When they don't see this, it relaxes back to the double exponential as it should. Now, when we increase this detuning to make it comparable to the line width of the photons, we start to see the beating signal, and we have a visibility of about 95% for this measurement. And when we further increase it, our side lobes have become higher, and And finally, when we increase it to about 10 times the line width, we see that this disappears. So this resolution is essentially limited by by the resolution of the single photon detectors. So these bins that you see is the jitter of the single photon source. And obviously we could resolve, if we had infinite resolution, we would still resolve the Wheeling signal. Basically, these measurements are showing that Bragg-Scattering is indeed only changing the frequency of the photon, but keeping all other properties of the input single photons identical. We also make a autocorrelation measurement to confirm that the two photons are bunching in the same arm of the frequency beam splitter. And of course, even without interference, the photons would bunch in the same arm with half the probability as they would with interference. And this is exactly what we're confirming here. We see an enhancement of about 1.3 for the case where the photons are far detuned as compared to the small detuning. So people have observed this with atomic systems many years ago. And now we are able to do this with better resolution of the single photon detectors and with relatively high Q microresonators that give us these few nanosecond coherence times in our single photon source. And finally, I would like to make a comment that that was just 2 modes. We can extend this to many modes. So if we add more pump fields here, we can get non-nearest neighbor interaction between different quantum fields. And of course, if we wanted to do arbitrary unitary transformation, we would still need of the order of n squared control fields, and the loss would scale as order n. This is similar to a typical UN to SUN to SU2 decomposition that you have with spatial schemes, but potentially here you could do this in a single fiber loop. The final application that I would like to talk about is how we can manipulate broadband inputs that are very narrow in time to do some picosecond level processing. So temporal modes are being looked at for photonic quantum information processing, and they are particularly important for applications that require strict synchronization in time. And what we want to do is use four-way mixing to zoom into some of these temporal waveforms. So the idea of a time lens has been around since the 1980s, and it's relatively straightforward. In analogy with a spatial lens, we have where a spatial lens imparts a quadratic phase shift in space. We have a time lens that imparts a quadratic phase shift in time, and this can kind of negate the effects of the diffraction and get a lens-like effect by having a process that imparts a quadratic phase shift onto our single photons. So and much like a thin lens, we can create an imaging system in time, and basically now the magnification factor is determined by the ratio of the dispersion or chirp that we apply before and after the time lens. So with Bragg-Scattering, how can we achieve broadband phase matching? What I showed before was just narrowband phase matching, but we can achieve broadband phase matching. So let's say we have one of the pumps is still CW, but the other is pulsed, and we put a strong chirp equal to 5P1, and on the other let's say we have a broadband input field centered at omega r, and now we have some chirp on it equal to phi r, and we write down our phase matching expression like we did before. Sorry about the typo, this should be P1. But we see that we get broadband phase matching if these two chirps have equal and opposite signs. And this condition is not difficult to achieve in experiment, and this will result in conversion of this broadband field to one single, to a narrow field at omega b. And this may look complicated, but this is essentially the same as what a lens does. If you put tilted plane waves on a lens, they would focus at different points that representing different k vectors. This is essentially doing the same things for Fourier transforming a broadband pulse to a narrowband signal at omega b. And so why should we care about this? It's because if our conversion bandwidth can exceed 5 nanometers, we can actually get the resolution, optical resolution of our time lens, which is inversely proportional to its aperture, to be less than a picosecond. So we did this with Bragg-Scattering, and this is what I'm showing. So we moved the pump, and with respect to the single photon fields, we've created them temporally synchronized, starting with a femtosecond laser that was spectrally broadened. And I'm scanning the delay, and we can see that it moves exactly like an object would if you moved it perpendicular to its optic axis. And we measure this amplitude, this magnification to be about 158. And we also show discrimination of single photon level pulses that are about 2.3 picoseconds in width and separated by 2.5 picoseconds. We created a very small delay by using a polarization maintaining fiber. And we can resolve them with detectors that have 100 picosecond jitter. The total jitter here is 350 picoseconds. That's because we do have a lot of jitter on our electronic side. But we see that with our magnifications, we can still resolve picosecond level pulses. And the last application, I probably don't have that much time, but the last application that I'd like to mention of this is mode sorting. So the process I described previously is very simple. It's just a imaging system, but we can do something more complicated with it using drawing inspiration from Fourier optics, in that we can generalize the phase imparted by the time lens to not just a quadratic phase, but to something more complex. And we can interleave these phases alternating with dispersion. And by this, we can actually change the intensity distribution of, let's say, a bunch of orthogonal Hermite Gaussian modes. And we can transform this to separated Gaussian pulses that can then be resolved. So basically, we can create a temporal mode sorter. And we actually did this using PyTorch, which does automatic differentiation for you. Automated differentiation for you over a large parameter space, which is what, and here are some of our results where I'm showing that basically starting with these orthogonal Hermite Gaussian modes, we can transfer them to separated Gaussian pulses. So you can send in 10 of these modes and resolve them simultaneously on the single photon detectors. In conclusion, I've shown you how we can make a frequency multiplex source with our efficient quantum frequency conversion. I've shown how we can achieve 2-photon interference with this using this process as a frequency beam splitter, and potentially this can be used in applications such as generating Bell states, GHZ states, etc. on integrated platforms. And I've also shown how we can do some temporal mode processing with this process. So I'd like to thank the people that I worked with at Cornell and Columbia, particularly Alessandro, Sven, and Stefan, who were postdocs that I worked with, and my advisor, Alex, Michal, whose group fabricated the devices that were used in this work, Anna, who we've collaborated with over the last 2 years, Avik from Stanford, with whom I collaborated on the Hong-Ou-Mandel project, and William, who fabricated the devices used in this project at the Cornell Nanoscale facility. So thank you so much, and I'm ready to take questions.
Thank you, Chaitali. Yes, if you have questions, please raise your hands or type them into the Q&A box, please. Okay, maybe I will start off with a question of my own. So this is a technical question. I believe there's also a lot of people in the audience who are not super familiar with these SPDC single photon sources. You mentioned this parameter called the CAR parameter, coincidences to accident ratio. Could you explain what that means?
So if you're pumping these single photon sources, so we are essentially post-selecting on the chance that on the 1-1 photon pair probability rather than on, like, it is always generating multiple photons, or also there could be noise coming from our pumps, and these could be adding contamination at the photon source that we are measuring. So the coincidences are likely to be dominated by, the true coincidences are likely to be dominated by the 1-1 possibility. And if you look far away outside the coherence window of the photons, the background is dominated by all these other processes. So the ratio is kind of telling us how well we're selecting on this 1-1 possibility that we want to.
And I have another question, which is more to do with the outlook that you talked about. So could you expand a little bit on prospects for scaling the tools that you mentioned to generate large-scale cluster states, etc., which are being talked about as essential ingredients for photonic quantum computing?
Yes, so it's quite difficult, especially because of losses on chip, and which is a big problem that needs to be solved. But one thing that we wanted to show with the, at least for generating one single photon, what we wanted to show that with much fewer resources, you can potentially, at least to some level, alleviate the problems of losses. Of course, if we are talking about using, if you're talking about, let's say, Bell state or G at Z state generation, there are actually ways to do this. So there is, so for example, if you wanted to generate Bell states with ring resonators, you could just make two rings with identical TM and TE FSR, like you could pump it, you could create two ring resonators that are identical in their free spectral range for the TM mode and the TE mode. And if you manage to selectively couple to each of these rings, you'll actually be generating a Bell state. So, and there's ways to do this for higher photon numbers. And so with kind of these integrated sources, you can come up with more neater and tighter schemes. Of course, there is always the problem of scale, of loss and scaling in quantum optics, which is difficult to solve. So, but hopefully the continuous effort to increase nonlinearity on chip and decrease loss, both fabrication and coupling, can at some point lead to much more scalable experiments than. Yeah.
Okay, if there are no further questions, I don't see any. I'd like to invite everyone who's in the seminar to our informal hangout post-seminar, like we've been doing these past few weeks. So you can find the link to do this in the chat window. It's on this gather.town platform. I guess at this point we can conclude the seminar and move on to that space.